Hi all. In this lecture, I want to talk about completeness in function spaces and what it means. So in Wednesday's lecture, we defined and we stated this theorem. We had this space of continuous functions, and we were restricting mostly to compact sets. We defined a distance as essentially the maximal difference in the function values. And with this metric, we stated that the space is complete. This is a stronger version of the statement that if you have a sequence of functions converging uniformly to a function, and these are continuous, then f is continuous. That statement is sort of the statement that x is closed. Now, you have to be a little bit careful with that statement that x is closed because x is the full space here. So the full space is always closed because it's always open. So in the terms of this class, we can't really say that, but a completeness is another way of expressing this idea that you have the limits are in there. Now, we'll discuss this more next Wednesday, but if you have one way of applying this, and this is often also how we applied in 131A, completeness is to series. The reason for that is that for series, it's harder to identify what the limits are. So suppose we're going to be talking about Taylor series. So we have a sum of x to the k over 2 to the k. And we look at, in our language, we're looking at the partial sum up to n. So this is fn of x. And we think of it, and of course, this is defined on all of the real line, but let's just restrict it onto 0, 1 for now. And it's a real valued function. Now, if you fix, now with this, we can talk about, does this sequence converge to some function? So in 131A, we saw that this sequence, once x is fixed, it becomes a sequence of partial sums of a series. And this sequence of partial sums converges to the infinite sum, for example, because you can compare this to 1 over 2 to the k. So by comparison test, this series converges. It's also a series of positive terms because x is in 0, 1. Actually, if you had x in minus m, you could prove that it converges, but let's not go there now. So now, okay, this converges. So this means that this is a real number for every x. So we can define a function, f of x is equal to this infinite sum. And with this, then f of x is the pointwise limit of the sequence fn. Why? Because limit as n goes to infinity of f of nx is equal to f of x. This is exactly what we were saying here. So this is also the difference between pointwise and uniform convergence. In the pointwise convergence, you get to fix an x at the beginning, whereas in uniform, you have to estimate somehow the distance between all x's. Now, this sequence also converges uniformly. So this is pointwise convergence because we fixed an x, but the sequence converges uniformly, and there the order is done a little differently. We have to fix an epsilon, and we want to say that the sequence converges uniformly as an application of this statement. But how we will do that is we will actually show that the sequence is Cauchy. Well, how do we show that the sequence is Cauchy? We have to fix an epsilon, where we have to find an n. Well, to do that, let's first write a relevant estimate. So if we're looking at difference between fn and fm of x, we are looking then at the difference from the sum from k equals n, k equals 1 to n of x to the n over x to the k over 2 to the k, and then minus sum from k equals 1 to m, x to the k, 2 to the k. Now you'll remember that if you have two different sums where the terms are identical, but they just go to a different index, like in 131A, what this can be represented as is a sum between these. So from k equals m plus 1 up to n of x to the k over 2 to the k. Well, for that, we will need that n is bigger than m, little m is bigger than some capital M, because writing it in this way presumes that m is less than n. Okay, so with this, now we can apply the triangle inequality. Pull it inside, just like in the homework number 1. You have 1 over 2 to the k here, and this term here you can estimate from above, certainly by 1 over 2 to the m. And if n is bigger than or equal to n, then this is less than or equal to 1 over 2 to the n. And we want this to be less than epsilon. So at this point, we have to choose our n. But it has to be done before all of this. So fix n is equal to, say, well, it should be like log base 2 of 1 over epsilon. But this might not be an integer, so we might need to choose a larger one. So we choose the ceiling of that. If you don't know what that is, Google. I have different, okay, so we estimated it with the usual way of estimating sums. And now we got that the sequence is Cauchy. Well, so what we get is that for all x, we have this estimate. And what this means is that, let's have a little space here. What this means is that distance infinity, f of fn and fm, is at most epsilon, because this here holds for all x. So epsilon is an upper bound for this quantity, and this is a supremum of that. And that's what we use. So this is equal to supremum over x of fn of x minus fm of x. And we know that these are bounded by epsilon, so the whole thing is bounded by epsilon. Okay, so what we get is that we get that fn is Cauchy. And therefore, because the space is complete, we get that the whole the sequence has to converge in X by the statement. We haven't proved that statement yet, but by that statement, we know that. So Fn is now Cauchy, and therefore, since X d infinity is complete, then Fn converges in the space. And this, in the space, it means that it converges uniformly. This was theorem from last lecture. But a small remark here is that it converges to some function g. Completeness gives you conversion to something. So we have two functions, g, that is converging uniformly to, and we have f, which we defined, which converges pointwise. Now, a small remark is that these have to be the same. And you should check this. And a hint for this is that this implies that Fn converges pointwise to G. And pointwise limits are unique. If you converge pointwise to 1, then you converge pointwise to the other. Okay, but this gives a way of saying that this sequence converges. This is a Cauchy sequence, first of all. It converges to the infinite sum, which is a function. And moreover, it actually tells us that this function is continuous because uniform limits are continuous. So this type of arguments and estimates become very crucial when you want to talk about series of functions. And that's the main topic that we'll delve into in the course of the next 2 or 3 weeks. So it's a preliminary. But let's go back to our main theorem that the space is complete. And there are 3 steps to this proof. There is a setup stage where we take a Cauchy sequence. There we have to identify what the limit of that sequence is, and then we have to prove convergence to that limit. This is generally the scheme of a proof of completeness. Because what does completeness mean? It means that every Cauchy sequence converges. So we take an arbitrary one, we prove that it has a limit. So there exists some x that we are interested in, and then we have to prove that it is a limit. So that's part 3. This is exactly like the correct answer on the first midterm exam. Okay, so we have our setup. Fn is a Cauchy sequence. And we want to define its limit. Now, this is a limit in the space of functions, so we need to define an f of x. As limit of fn. Well, what is f? F of n? F of n is a function. So f is a function from 0, 1. And defining a function is the same thing as defining its values. And so how do we do that? Well, let's fix an x in 0, 1. We will define f of x as follows. Define f of x as the limit of fn of x. Now, we cannot just say that without saying anything. Why does the limit exist? So why does this limit exist? The limit of fn of x exists, and this is a limit in n, by the way. This is when I say limit here, I always mean limit in there. Of fn x exists since it is Cauchy. Well, why is that? Well, let's fix an epsilon. So indeed, we want to say that it is Cauchy. So let's say indeed, fix an epsilon positive. Then we have to use something that we know. So we know that it is a Cauchy sequence in X. So there exists an n. This comes in here. So there exists an n such that if n is bigger than or equal to n, then distance infinity between fn and fm is less than or equal to epsilon. And it should be m and n are bigger than n. If you want, sometimes you can make one of these indices bigger. This is usually useful for series, but now we don't need it, so it doesn't matter. So, and it's symmetric in n, symmetric in m and n, and that's why you can do that. But okay, m and n, so if m and n are bigger than n, so using the same n, what we get is m n bigger than or equal to n implies that fn of x minus fm of x, which is less than or equal to sup over all possible values of fn y minus fm y, and I'm using y here not to confuse myself with the previous x. This here is equal to the distance between them, which is less than or equal to epsilon by choice of m. And that concludes this subpart. So we know it's a Cauchy sequence, and we know that the limit exists, and this defines fx well. Okay, so now we have a function to work with, and we have now f of x is defined for all x in 0, 1, and limit n goes to infinity, fn of x is equal to f of x pointwise, so meaning for every x. That's what that previous part showed. But now we need to show that fn converges uniformly to f of x. And therefore, if it converges uniformly, we can use that the limit function is continuous, because at this point, we don't even know that f of x, as we defined it, is continuous. So let's show that it converges uniformly. Let's fix epsilon positive. Now there exists an n from the Cauchy condition such that if n and m are bigger than or equal to n, then fn of x minus fm of x is less than or equal to epsilon. Now, fix n bigger than or equal to n. I mean, we are wanting to estimate n. Then, since absolute value function is continuous, if we look at fn of x minus f of x, this is the same thing as limit as m goes to infinity of fn of x minus fm of x. And I'm saying here that you fix this n because n is not playing a role in this limit, it's in m. Now this quantity here is converging to that, and that's convergence of real numbers. This here is a constant, so therefore we get this property. And this holds for all x. We have this, all x fixed, we have this. Okay, but what do we know about this? Here, these are less than or equal to epsilon. So we get that for all x in 0, 1, fn of x minus f of x is less than or equal to epsilon. But this holds as long as n is bigger than a capital N. So we've shown uniform convergence. So since fn converges uniformly to f, then by theorem from last time, from Wednesday, f is continuous. And by theorem from Wednesday as well, f is in x, and fn limit n goes to infinity is equal to f in the metric space xd infinity. Because why? Because we showed that convergence in xd infinity is the same as uniform convergence, and we just concluded uniform convergence. So we're done because we showed that this arbitrary Cauchy sequence converges.